Good morning, everybody. I hope you guys are doing well today. Today, we're going to talk about some applications of logarithms, kind of similar to what we did in the last section. These ones, though, I think are a little actually easier to understand than the last word problems from 5.3. So let's get started. Uh, the first problem we're going to look at is about doubling an investment. So it says you invest $500 at an annual interest rate of 6.75%, and it's going to be compounded continuously. How long will it take your money to double? And so what we need to utilize for this problem is actually one of our interest formulas. And I know it's been quite a while since we discussed those, but with this one, because we're talking about continuously compounding interest, we're going to use the APERT formula. That's A equals P e to the RT. And so in case you don't remember, let me refresh your memory. A is your account balance, P is the principal, E is the actual number E. It's a button on your calculator, but it's like pi, so it's 2.71828. And then R is the rate, and it needs to be in decimal form. And then T is time in years. And so we need to utilize this formula and plug in everything we know. So let's start with 500. 500 is the principal amount being invested, so that's going to go in for P. The rate is 6.75%. That needs to be converted into a decimal. So you're going to move that decimal point 2 places to the left, and you'll put 0.0675 in for R. Time is actually what we're trying to solve for because it's asking us how long will it take your money to double. The last part here, money to double, that's your key kind of hint that we still need to fill in one of the other variables. So we know the P, the E's a number, the R's filled in. Time is what we don't know. The account balance, what we're looking for is the money to double. So if you start with 500 and you want it to double, it will turn into 1,000. So what you can see is 1,000 goes in for your account balance because it's doubling. We started with 500 and we're investing that at 6.75%, but that percent is written as a decimal, and we need to solve for t. So in order to solve for t, you can see that this t is up in the exponent position. And anytime you have a variable in the exponent position and you need to solve for that variable, it is going to involve logarithms. That is what logs are for. They are for solving variables that are up here in the exponent. So what we need to do, though, is we need to peel back a little bit of a layer here. We only want the base and its power to be on the left-hand side. We don't want anything multiplying, adding, subtracting, dividing over here. So we're actually going to divide both sides by 500 first. And when we do that, you can see now we have e to the 0.0675t equals 2. Now, we need a way to bring this power down. And in order to do that, we're going to utilize the power property. Before we can utilize the power property, however, we need to have a log in there. So we are actually going to use natural log. The reason being is the natural log base is e, which matches the base of our exponent. So we're going to take the natural log of both sides. Take the natural log of this, and then the natural log of 2 over here. And you're allowed to do that. You're keeping your equation balanced because you did the same thing to both sides of the equation. Now we're going to utilize the power property, as I said before, and we're going to bring this 0.0675t down and in front of the natural log. And you'll notice we have natural log of e, which hopefully you remember is 1. So that actually cancels out. Natural log of e goes away, and we're just going to be left with the 0.0675t equals natural log of 2. And from there, it's relatively simple. You're just going to divide both sides by 0.0675. And when you do that, you get an answer of approximately 10.27 years. So a little tiny bit, about 10 and a quarter years, just slightly over 10 and a quarter. In 10 years, your investment will double. And here is a graph of that equation, and you can look at the $500 and where would it be after each year, 1, 2, 3, 4, 5, 6, all the way up to 10. You can see that it doubles. And notice the growth is happening, but it's not crazy growth yet. And remember, if you recall, whenever we discussed investing money, your big growth happens after a long period of time. So that's why it's important to start putting money away early. All right, the second one we're going to look at, it says the retail sales Y in billions of dollars of e-commerce companies in the United States from 2002 to 2010 can be modeled by this equation. Y equals negative 566 plus 244.7 natural log of T, where T is in between and including 12 to 20. Remember, this is only for 2002 through 2010. I think as you would probably thought through this problem, you would realize that the e-commerce has only gotten bigger and bigger and bigger. I mean, just look at the world's richest man is an e-commerce person, Jeff Bezos with Amazon, and you can see malls are closing down all over the place. So I would be curious to see if this was, extended till another 10 years and see where we would be at. But it says T represents in this equation the year with T equals 12 corresponding to 2002. It says during which year did the sales reach $141 billion? And so if you go over here and you can see 141, there's 140. So it's going to be slightly higher. We go straight over. And then if we went down, it looks to be 18. And the number 18 would correspond to 2008. Now, how do we know for sure? We looked at the graph. Okay, here's how we actually are going to figure this out for sure. We're going to take this 141 billion, which is the retail sales, and plug that in for Y, since Y is what represents the retail sales. So we're going to take our equation. We're going to plug in 141 billion. It's actually just 141 because Y is in billions. And now we're going to solve this equation. So the first thing we're going to do, remember, as I said in the last problem, when you're solving these, you really only want the base and the power, or you just want the log by itself. If there's anything else here with the log or natural log or the base and the power, you need to get rid of it. So we need to get rid of this negative 566 first by adding that to both sides. Following that, we're going to divide both sides by 244.7. And now you can see we're left with natural log of T equals 707 over 244.7. Now, what you're going to do here is actually convert this. You can skip this step right here because I actually don't quite do it this way. You can do it this way if you want. But what I prefer to do is anytime, if you look at this third line right here where my pointer is, if you have a log or a natural log of a variable, once that's stripped down and that's the only thing that's left, take it from logarithmic form and put it into exponential form. It's the very first log property that we learned. So you can see this is log base E, which is why it's natural log. So it's the base of the log becomes the base of the power. So it's going to be E to the 707 divided by 244.7. So E to that power equals T. So we're converting it straight from logarithmic form to exponential form. You can skip this step right here. So it becomes E to the 707 divided by 244.7 equals T. And so that right there, when you type that into your calculator, is going to give you your answer. And you can see it is approximately 18. And that's exactly what we thought from the graph. So there you go, guys. Those are the two examples I have for you today. Hope you're all doing well, and I will talk to you soon.